Okay, welcome back. Just to pick up where we left off, so using this sort of molecular motif, the PITN, some of the first attempts at low bandgap polymers were actually done about over 10 years ago, and these are synthesized by the group of Dirk van den Noygden in Belgium, Leuven, Belgium. And the idea was to incorporate this isothianapthene into the backbone of the polymer. So the polythiophene backbone was known for 20 years before that. And the idea was to try to reduce the band gap by putting in some component of the isothianapthene, largely to decrease this bond length alternation delta R, get a lower band gap. So what happens is, depending on how many and how frequently you put in isothianapthene, and what end groups you put on it. So if you put chlorine on the end group versus a sulfur bridged alkyl group, you can tune the band gap quite substantially. So in this family of molecules, you can get band gaps ranging from 1.3, quite small value, up to 2.1. So these are some of the earliest low band gap materials, and they did show nice optical properties in a lot of cases. I'm not going to go through this in great detail, but here are optical absorption spectra. So here's P1 with this band gap of about 2/2. Here's P3 with a band gap closer to 1.3. And then P4 and P5, they seem to have very broad absorption spectra. That indicates that they're actually heavily doped. They're not very pure materials. So you start to get absorption in the infrared. So the P1 and P2 and P3 from the previous slide, those are the ones that we tried to really make devices from already over 10 years ago. So the good thing is we did get spectral photocurrent from lower energy, higher wavelength photons, but overall device performances were very poor, and as you can see, fill factor is quite low and efficiencies quite low. But nonetheless, those are some of the first low band gap devices that were made. But shortly thereafter was the development of a new type of low band gap system. And this is the push-pull donor-acceptor intramolecular system that Andrew Ferguson talked about last week. And again, this was a slide for him. So the idea is you put in two different molecular moieties in the polymer itself, one that tends to push electrons, one that tends to pull electrons. And what that creates is an intermediate, let's say, resonance state that has a reduced band gap, so-called push-pull low band gap material. So these were first really developed for the purpose of OPV by René Janssen's group in Eindhoven, and this PTPTB was the first true low band gap material using this technique. So the band gap in this case was something like 1.6 electron volts, and the original efficiency was something like 1%. So it was not super high, but had a nice spectral response. So since then, people have taken that motif and really run with it, like Andrew talked about last week, and can do this with any variety of groups of materials. So here is a push-pull material. Here's this polycyclo benzene in this case, and here's this benzodiazole BDT. So electrons are pushed from here to here. In this case, again, electrons are pushed from here to here. And we can tune band gaps, in this case, down to below one electron volt. More recently is this PCPD-DBT, or TBT, that I explained in the beginning. And this had a low band gap going down to about 1.4 electron volts, just about optimal. And that really opened up the pathway to tandem devices, where you would make two junctions, absorb the low energy photons in one junction, absorb high energy photons in the other, in this case from P3HC, combine the two and get an efficient device. And as the final example, I just go back to the UCLA paper of 7.4% with PTB7. This is also a push-pull material. So electrons are pushed from here into this thiaphenes, which is electron-efficient material. So push-pull is our dominant way of tuning band gap. However, there's actually a much more simple way of tuning band gap, which is if you just consider these polymers as a box of electrons. If you just do a simple quantum mechanical one-dimensional box, you can estimate the energy of the particle in the box. And so as you make the polymer longer, box gets bigger, energy gets smaller, and that means you push the lower wavelengths. So these dicyanovinyls substitute oligothiophene. That means there's a oligothiophene in the middle and then cyano groups on the ends. This is commonly used to tune the band gap and get a wide range of spectral responses. So you're going to hear Moritz talk more about this as well. So just want to wrap up and also preface some more future speakers, namely Ross Larson and Charles Musgrave, that we can really calculate the electronic structure of these materials very well using computational techniques. So largely this is density functional theory, but there's a whole host of other techniques, more ab initio techniques, that we can use to compute the exact value of the band gap, or at least pretty close. Of course, with these we can compute what the optimized structure is. So this is a oligomer that has a phenyl group, 3 thiophene groups, and then a lower band gap moiety. So we can optimize the structure, compute the HOMO and LUMO orbitals, so you physically see where the densities of those orbitals are, and then look at the transition density. So when you go from one to another to create the exciton, where are those transitions, and where does charge migrate in the molecule when you absorb the light, so the charge density difference. So in this case, electrons are moving out to the N group. This is the electron deficient material, the puller, and you can see that's evident in these diagrams. So just want to point out that there's a lot of very specific calculations that can be done. We can get quite good values from these types of things. When we want to consider things like exciton transport, charge transport, we need to look at the overlap of the HOMO orbitals between adjacent molecules and compute the overlap integral between those two. Typically that value is quite small, something in the order of 0.01 electron volts. We know it's quite small because if it was large, then we would have very good transport. We would have band-like transport in these materials, just like in silicon. We don't have that. Those overlap integrals are less than kT worth of energy. Right? kT is about 0.026 electron volts. So it means that the molecules tend to be more isolated, and we require thermally stimulated hopping to get charges between the polymer chains. So that was a bit of a digression, but you know where all those numbers come from. Okay, so I want to talk about the photophysics at a very basic level and then go into the device physics at a slightly more detailed level. So some of the original measurements on these blends, and this in particular is the bulk-heterojunction blend, is to look at two things. One is the luminescent intensity of the polymer as a function of how much fullerene you put into the system. How much PCBM. So PCBM was the soluble version of C60, right? So as you increase the PCBM concentration, the luminescent efficiency decreases quite rapidly, right? So you're quenching the exciton, dissociating it, before it has a chance to decay radiatively. That happens at very small concentrations because the excitons can easily find a fullerene even at 1% concentration. Now, if you take that blend and put electrodes on the top and bottom and extract the current out of the device, what you find is that at 1% concentration, you really don't get much current out, right? You've got to exceed the percolation limit of the fullerene in the polymer matrix in order to get current out. And so you've got to get up beyond about 15% fullerene before you start seeing sizable photocurrent generation. So this is the basic idea for the blend. And when optimizing a device, you would choose a blend ratio closer to this side so that you would get most of the excitons dissociated and yet get most of the charges out of the device. So another way to look at it is from a kinetic standpoint. What are the different processes that can occur and what are the pathways? So the standard pathway would be that the donor absorbs a photon, photonic energy, to create the excited state D star. Then we could have several loss mechanisms, either through luminescent, this should be radiative KR, or non-radiative KNR loss mechanisms. We don't want those. We want the exciton to diffuse to the interface with the acceptor and undergo a series of steps. So it's not fully understood what these series of steps are. We're going to hear a lot more about this from Jiayang Zhu at UT Austin. But generally what happens is that the exciton delocalizes across the polymer and the fullerene for a brief instant, and then you get partial charge separation, which is that pause state that I talked about, the charge transfer exciton state, the CT state. Another way to call it is the bound radical polarized state, the DRP state. So from there we get the full charge separation and then transport out of the device. So I just want to talk about this, this step right here quickly. And I do mean quickly because it's this 45 femtosecond process. So the way we measure this is with ultra-fast pump probe measurement. It's called photo-induced absorption. So the idea is that we monitor the absorption of the system on a femtosecond time scale after a photon has already come in and pumped or excited the system. So we pump it with a 7 femtosecond pump, and then we probe it with longer time scales. So at first you see this gray peak here, and what the scale is delta T over T. That is the change in transmission over the original transmission. So a positive value means more photons are going through the film. So why would that happen? Actually, let me ask you guys, why would that happen? Why would we have a positive delta T over T here? What would explain that? We have a lot of excitons in the system.
Or the excitons are producing the photons again?
So there's already excitons there.
Right, and they're just radiatively emitting, so we're seeing more transmission?
They are radiative emitting. You're not seeing that in the delta T over T, however. So if you have a lot of excitons in the film, how many states are available to absorb more excitons? Lower value, right? So in fact, there's simply less molecules that are available for absorption, so you get more transmission. This thing's called bleaching, right? So you bleach all the color out of your t-shirt. You can also bleach the excitons out of the material. So positive delta T over T is bleaching. Now what happens, and these are time slices in femtoseconds, is that you start to see a negative delta T over T. So that indicates absorption, right? Some of the photons are truly being absorbed. And you notice that these are at longer wavelengths. So that indicates that a new species is absorbing in the film. And that new species is the charged state of the material. So you're starting to see the exciton dissociating the charges, and that absorption feature is due to the absorption from those charges, or those polarons, right? A polaron is the charge in its surrounding matrix of associated charges. So anyhow, you can resolve that in time, and what you see is a decay of something like 45 femtoseconds. This was measured, again, about over 10 years ago by Christoph Robetz between OPV and PCBM. So now it's time for yet another quicker question. So in this case, what we did was we put an exciton on the polymer, and we had an electron transfer to the fluid. So I'm going to ask you to just make a guess. And you have no real reason to know the answer, but I want to see what your intuition is. So if we do the reverse process, if we put an exciton on the fullerene, and we have a positive charge, a hole that it transfers to the polymer, we think it's slower, faster, about the same as the process I just showed. So I started the clicker. How about 20 responses? These types of questions will make the race for the prize at the end a little more uniform, I think. Okay, I've got 50 responses. Let me go ahead and stop it. 3, 2, 1, stop. And then I need to kick out of my program here. Okay, so more than half said a little slower than the electron transfer. Well, that should be a little slower. When I was writing this, I was a little slower. So actually, the answer is B. It's a little bit faster. So in that direction, it's actually 30 femtoseconds. And Case Homelin and his colleagues have measured that. So we don't really know why that is, but it might have to do with the rigidity of the buckyball, the C60. It's a very rigid molecule. And that means its reorganization energy is very low. And I'm going to talk about that in a bit as well. But yeah, it's actually faster. So very fast processes in both directions. Okay, so how do we actually measure the long processes? So I showed you how to measure the fast processes on a sort of 10 to a couple hundred femtosecond process. What if we want to measure things on a microsecond, millisecond to microsecond time scale? Well, there's lots of techniques. The one we like to use at NREL is called time-resolved microwave conductivity, TRMC. So this is really developed by Gary Rumbles and his group, and Nikos Kopidakis. And it was borrowed originally from Delft University, the group of John Morgan. So I won't go into details, but the general idea is that you take your sample, which is the polymer film with no electrodes, and you put it into a microwave cavity. So a little metallic cavity, 15 centimeters wide, a few centimeters in either direction, and you irradiate it with microwave beams. At the same time, you come in with a pulse of light and create a population of charge carriers in the film. So these charge carriers increase the dielectric constant in the material, and that attenuates or absorbs the microwaves. So you get an incoming signal of P, and then you get an outgoing signal of P minus delta P. And so from that difference, what you can measure is the change in photoconductance of the material. There's a proportionality factor there, K, which is a geometric proportionality factor. So you get a change in conductance, delta G. You can break that down further into components that depend on N, the density of electrons, times mu E, the mobility of the electrons. Right? Mobility is velocity divided by electric field. And then also the hole density P times the mobility of the holes. So then what you get is a sum of carrier densities times mobilities. There's some other factors there, quantum efficiency, fraction absorbed, but all that we can calculate out. In the end, what we want to get are these values, NU plus PMU. So we can do that, and here's a standard example. Here's P3HC, PCBM, blend of the two components. So at 0 time, when we hit the system with the pulse of light, we measure that delta P in the microwaves and get out what is phi, the quantum yield, times the sum of the mobilities. And what you see is a rapid rise in the signal. So this is the inverse of the decrease of the microwaves is an increase in the conductivity. And then you monitor that over, in this case, 150 nanoseconds, and in fact out to micro and milliseconds. So indeed, what you see is that the carriers that were photogenerated in the beginning are very long-lived. So that's that 1 microsecond I talked about in the beginning. Separate the carriers very quickly, yet they're metastable and do not recombine for a very long period of time. In this particular case, what you see is that as you increase the intensity of the light, so here is 10 suns, right? A sun is a kilowatt per meter squared, so this would be 10 kilowatts per meter squared. As you make that even higher, so go to 10,000 kilowatts per meter squared, or 1,000, you actually see the signal go down. And that's for a different effect. In that case, what happens is that the excitons, there's a high density of excitons, and they interact with the carriers, and that quenches the excitons. So in fact, the lifetime goes down greatly at very high intensity. But we only have to deal with one sun for the most part, unless we're going to concentrate the light. Okay, so this brings about one of the big mysteries in OPV, which is still not solved. So we have a dilemma. The dilemma is that the dielectric constant for organic semiconductors is rather small, something around 3 or 4. Whereas in silicon, it's about 9, other materials, it's much higher. And what that means is that the Coulomb capture radius in organics is very large, right? What's the Coulomb capture radius? That's the distance that you should pull the carriers away from each other so that their binding energy becomes smaller than KT, right? If it's smaller than KT, then thermal energy will oscillate these guys and they'll basically bounce away from each other. So in order for that to happen, we would need to move the electron and hole 18 nanometers away. But I showed you from the TESs that the polymer and the fullerene tend to be actually much closer, and the average domain size is really just a few nanometers. So the question is, how do we get carriers out of these devices? And that's been studied for quite a while, and as I mentioned, is still a topic of debate. Well, this goes way back to 1938, and the work of Onsager, who very prestigious theoretical physicist. So he first studied charge separation of electrons and holes in a homogeneous system. So in one material, not the donor and acceptor blend, but one material, how do we separate the charges? So this gets a little bit equation-y, so I'll just go through just sort of cursory for right now. But one can imagine this is the hole, this is the electron. They're in the presence of some field, F. And there's a dipole and some angle relative to the field. So first we can compute the energy of the charges. That's just E squared over 4 pi epsilon times the distance r. And what you get is a rate for charge separation that goes as an exponent of that energy. So this looks like a Maxwell-Boltzmann distribution, which is what it is. So you take this delta E, stick it up here, take the exponent with 1 over kT. And then you've got some other factors that deal with the average mobility of the two and the average dielectric constant. Right? So if they're very mobile, they can get away from each other faster. But importantly, you see dielectric constant is on the bottom. So a small dielectric constant here means the rate of, anyway, this is actually rate of recombination. So the rate of recombination goes up as epsilon goes down. There's some other factors there which I'm not going to deal with. The field strength comes in this B term, which goes into the KE term. Look at the slide afterwards or come talk to me. What happens is that this works well in electrolyte solutions, where you've got basically very strong electric fields. You take a salt solution like sodium chloride, apply a very strong electric field. This equation works quite well. But it doesn't really work for the types of donor-acceptor systems that we're talking about. And if in order to use this, we would find that the field dependence is much larger than it comes into these equations. So this model doesn't quite work. So more recently, in the 80s, there was an extension of this model by Charles Braun back in '83, where he said, okay, let's use this Onsager model, but let's use a more accurate description of the available states, the kinetics of the system. So instead of just an electron hole that can either move away from each other or not, let's consider that there's an intermediate state, this charge transfer state, or bound radical polaron, which is basically kind of a middle state, a reservoir, which we can get free carriers from, or can recombine into the ground state, right? That K factor. So Braun carried this out, and he included something called Langevin recombination, another famous theoretical physicist, physical chemist. And so Langevin recombination says that as the carriers move faster, they're more likely to find each other. So as the mobility goes up, the rate of recombination goes up. And if there's more of them, there's more electrons and more holes, n times p, they're more likely to recombine. So basically, as the charge density goes up, the recombination rate goes up. So Braun included this in the calculation and then calculated what would be the probability for the carriers to escape from each other, P of V, as a function of the electric field, in this case the log of the electric field. And so what you get is a low electric field, it's kind of flat, there's a sharp turn on, and then you saturate at basically 100% escape. So in fact, this theory fits pretty well. So if you have a single material, again, not a donor-acceptor system, a single material, apply electric field, you can get carriers out of it, and it fits this model quite well. So Peter Poymans has done these calculations and experiments, and it fits pretty well. However, there's another problem. This requires strong electric fields. And if we go into the device, and this starts the device physics part, it turns out that we don't have very strong electric fields when we operate the device. So let me explain that. So we have to develop a band structure for the device. So what we do is have our contacts. Here's a positive contact, so the gray stuff is just an electrode. Negative contact, and they're shifted from each other. So this is now a metal insulator metal, right? Metal insulator metal. And so we put in the donor and acceptor, the energetic levels. So we have the HOMO of the donor and the LUMO of the acceptor. Those become the functional bands of the active layer. You can more or less ignore the donor LUMO. So this is the effective band gap of the system. So you make contact with the device, put it in short circuit, which means that the Fermi level lines up. And what you get is a very sharp bend in the band, or sharp angle in the band, which means a high electric field. So in this case, there's a high electric field in the band gap. Now, under open circuit conditions, these bands become much flatter. It means there's basically no current coming out of the device, and there's basically no field. I've made a simplification. There's actually a little bit of field, but not much. So first of all, how do we get that open circuit voltage? Well, what happens is we come in with the photon, we create electrons and holes, and they induce what are called the quasi-Fermi levels, Fermi levels. So a Fermi level is just the chemical potential, right? In this case, the chemical potential is the flat line here. The quasi-Fermi level is the chemical potential of only the electrons or only the holes. You do kind of a statistical trick and define them separately. So you've got quasi-Fermi level for electrons, quasi-Fermi level for holes. And it's the splitting of those two that gives you the voltage in the device. So as you put more photons in, you get more splitting of the Fermi levels, and you get more voltage out of the device. So in general, more light intensity means more voltage. Now, if we go and look at the device, so here's the same JV curve I showed before. We operate the device at the maximum power point, where we would get the most power out. So at short circuit with a 0 power, open circuit is 0 power, we need to operate right there, right at the maximum power point. But maximum power point is pretty close to VLC. It's pretty close to that picture there. So basically the fields as we're operating the device are quite weak. So the previous equation, this Onsager thing, that also does not apply because we're not in the high field regime, we're more in the low field regime. So again, we're stuck with our conundrum. How do we actually get charges out of the device? And the answer comes down to A, a mixture of donor and acceptor to produce these nano domains, and B, very complicated charge transfer dynamics that allow for the charges to separate. That's the subject of another talk, and again, Jiayang Zhu is going to give you a lot more information on that, as well as other speakers. Okay. So, and the bottom line is the electric field dependence on the device is actually pretty weak. Okay, so just a little bit of the device physics here. We can model these devices using pretty simple drift-diffusion equations. So we develop differential equation. We have the diffusion term, so second derivative of the carrier concentration. A drift term, which is the first derivative, and here's electric field. A recombination term, you see the negative sign there. And then a generation term, which is due to light absorption. So there's an exponential term here, which is the Beer-Lambert law. So we can stick this differential equation, or we can stick in the numbers, we can solve it. And if you then calculate the current as a function of thickness, you get what you would expect. So a thicker device gives you more current, up to a point when the recombination starts to balance the production, which you reach a maximum, and then you come back down. And in the model, if you increase the mobility of the carriers, in this case from 10 to the minus 2 to 10 to the minus 4, all the way around, what you see is that this position of maximum current shifts to higher thicknesses. You can make a thicker device that also gives you more current. So at least in the simple model here, mobility is a good thing. Okay, any questions on this relatively simple device model? We're going to do a little more detailed one in a second. This is for me lecture 2, so I'm running a little bit behind. Yes, please.
As you know, we don't have electric field, we don't have electric field active diode. And most of the model use the Onsager ground model. I don't know if it's correct or not, and it's correct. Because it's the electric field, if you see to the equation,
So the
coming back.
yes, the question is, correct me if I'm wrong, is that why don't we use Onsager in this equation, and how can it be right if we don't use it?
No.
No?
Dissociation rate from the exciton to
Yeah.
the free carriers, okay?
Yes.
The formula is field dependent, okay? Which actually there is some debate that we don't have electric field inside the active diode. That means this model is correct or not? If yes, if not, which kind of model we can use instead?
Well, this simple model assumes that every absorbed photon creates charges. So the field dependence with charge generation is not in this whatsoever. Most of the experiments that I've seen have shown very weak dependence of charge generation on electric field. So that it's not electric field driven. It's driven by the kinetics of the charge transfer process and the energetics of the charge transfer process. In particular, Marcus theory. And that's the last section of my talk, right? So Marcus theory is one of the main driving factors for the charge separation. So at a device level, you can do the device model without any field dependence on charge generation and get a pretty good answer, get a pretty accurate answer. Yeah. So you can ignore ensemble and Braun at that level of calculation. Thanks, yeah.
The dilemma which you talked about, it was not very clear for me. Can you explain a little more about that dilemma?
About which?
Dilemma, the dilemma.
I'm sorry.
About the related permittivity, which is 3 and 4, 2 and 4.
Where are we? Which slide do you want to look at?
Back. Yes.
Exactly.
Yeah, dielectric constant issue.
Yes.
So organics have this low dielectric constant. So that means in order to liberate electron in hole, you would need to separate them by something like 20 nanometers. That would be a sizable proportion of the device thickness. The active layer is 100 to 200 nanometers. So in reality, this is not going to occur. Somehow, in the device, we get liberated charges that are much closer together than 18 nanometers. So in fact, they can be 2 or 3 nanometers apart, and they are essentially free charges. So the question is, why aren't they still bound coulomically? Or why doesn't the coulombic attraction prevent them from being extracted out of the device and get free carriers? So the answer is not in electric field per se, but we think it's in this Marcus theory description and in the kinetics. So again, that's the last section of my talk. Does it help? Yeah. Right, so in silicon, dielectric constant is 9. So in that case, if you separate the electron hole by a nanometer, then they're beyond the Coulombic capture radius and they're free charges. Not a problem. Right? So this is the fundamental reason why these materials are excitonic materials, and electron and hole are not free, but they're bound. Good question. Okay, so a little more detail, and forgive the busyness of this slide as well. But if we want to do that drift diffusion model at a deeper level, then we can go and solve those equations, not on average, but at each point in the device. And we would solve the fundamental equations, so the Poisson equation, continuity equation, drift equation, diffusion equation, drift equation, and so on. Do that for both electrons and holes at every point in the device. So we can do that. What we're doing is borrowing a model from the Time Coaster that was published about 8 years ago. And this is actually carried out at NREL, I should point out, by Peter Graff, who's in the Scientific Computing Center. So I just want to point out in this equation, so this is Poisson's equation, so a second derivative of the potential, V of x, is proportional to the charge density, right? Either the electrons as a function of x, or the holes as a function of x. And the proportionate constant is the charge over dielectric constant. So what we're doing in this model is we're also incorporating some extra charges, C of x. So C of x in this case is basically a constant. And these are defect carriers, dark carriers present in the film. We're going to talk about those in a second. Okay, so just for this particular model, we actually used the kinetic scheme that Braun had used already back in the 80s as a way of describing the overall charge generation. And again, the field dependence isn't quite right in this model, but as a kinetic scheme, it works. So if we consider there's a rate of dissociation from the CT state to free carriers, that's K dis, K dissociation. There's a rate of recombination that goes back, that's this Langevin term we talked about. And then there's a rate of recombination to the ground state, a loss mechanism. We just input those parameters into the model. We can get a rate of free carrier generation at a given point in the device. So it's not necessarily accurate in the details of the physics, but qualitatively it gives you the right result. So we can do that. We put all those equations into the computer. We can put in a bunch of parameters, including the density of states, the generation rate, that's the amount of absorbed photons per second, recombination rate, electron density, or hole density, man gap, electron density. Stick all that stuff in, and if we got it right, we can simulate a JV curve with pretty good accuracy. So this is real data overlaid with the model, and this was a 7% device that was made at Enron. So what did we learn in the process? Well, if we didn't measure some of these coefficients to begin with, we probably wouldn't learn very much. But what we need to do is measure at least some of them beforehand and then fit other ones, and that can tell us a little something about the system. In this case, we have a good handle on the recombination rate. We can measure that with the TRMC I talked about before, and we can measure electron and hole mobilities through a variety of techniques. So now it's time for clicker question number 4. You can tell I really have some obsession with the clicker question. It's kind of fun. I'm going to ask you another hard one. So I talked about that C of x, this constant term in the equations. You put in dark carriers. The question is, what do these dark carriers, what do they do to the device in terms of the short circuit and the efficiency? Again, if you're not a device physicist, you probably don't know offhand, but let's see what your intuition says. Oh, I need to hit start. Okay, I just started.
C and D.
Oh, C and D is the same. One of them should be, sorry, this should be increases. So D should be efficiency increases. Sorry about that. Got about 30 responses. Okay, a few more seconds. And I got 50, so we'll stop it. Okay, so, well, we've got a little advantage to C, otherwise kind of a flat distribution. So in my undergraduate classes, I would call that a rainbow assortment and have you guys discuss and debate. We won't do that here. But so actually C is the correct answer. So the short circuit decreases and the efficiency decreases. And just to give you an example, so here's the same JV curve that I showed before. And now what I'm doing is I'm turning up those dark carriers. I'm increasing C. So these are carriers that are basically impurities in the film that are already there. They're not photogenerated. And they're affecting the device performance. And as you make them more and more dense, so up to 10 to 17 per cubic centimeter, you see there's a large decrease in the short circuit current. Open circuit voltage stays about the same, and decrease in efficiency. So they make the device worse. So the question is, why is that? And well, let me ask you guys, why might that be? What would the dark carriers potentially do to the device physics? Increase recombination? Yep, they definitely would. So if you put in an excess of holes, then the photo-generated electrons would recombine with those. So that's one mechanism. That would decrease the short circuit current. Yes. Any other ideas? What about the field distribution in the device? Non-homogeneous, right? So I showed you the metal insulator metal picture where a homogeneous field. That's going to change if you start putting in these carriers. So what happens is that those carriers, the dark carriers, if they're near an electrode, they can get depleted, extracted out of the device, and that's going to alter the field distribution. So what I'm showing here is on the left is the potential as a function of x. So this is 120 nanometers. This is the potential. So with no carriers, the potential is more or less straight. A little bit of bending at the edges. That means the field, which is the derivative of the potential, is uniform. And here are the electron and hole densities also uniform. So you start to turn up the dark carriers, go to 1 times 10 to the 16. You can see a little bit of bending here, a little bit of flattening, a little bit of bending. And let's go all the way up to 10 to the 17. And what happens is you've collapsed the field, so all the field now is on this side of the device. That happens to be the negative side, and there's no field here. Now we said that the generation rate is relatively independent of field. So we could still say that the generation rate is constant throughout the device. But the extraction rate the amount of charges you get out before they recombine is definitely not independent of field. All right, it's strongly field dependent. So here we can pull all the carriers out very rapidly. Here we can't. And we basically wind up with a buildup of carriers here. So then we get lots of recombination, we lose charges, and we get a buildup of charge, and generally the current becomes much worse. So in general, these dark carriers are a bad thing for the device, and we want to get rid of them. Unfortunately, we do have to deal with them. So particularly in this P3HT, we have quite a few of them. Something like 5 times 10 to the 16 is what we measure. So some intermediate picture between this one and the last one, and it is something we need to deal with. Okay, so I'm going to skip the next section. I've got a few slides that talk about the experimental part of that, but let me go to the Marcus theory section. So here, yeah. So this is a more detailed description of the charge generation using this Marcus theory stuff. So I'm going to just base this. I'm going to base all my calculations on this paper. I've just shown it 3 times now. 7.4% paper based on these 2 materials, PTP7, and this is a C70 version of PCBM. So first of all, just taking a look at this system, we can think about some of the thermodynamics of this system. So what we can do is look at the quantum efficiency, that is the electrons out for photons absorbed, and see that it's about 60%, pretty flat, all the way up to 750 nanometers. Right? That's the experimental data. What we can do is separate out the 2 components of that. The red curve is photons absorbed in the fullerene, blue curve is photons absorbed in the polymer. And I said in the beginning, or early on, that both mechanisms could generate current. In fact, it's even more efficient if it's absorbed by the fullerene. So in the end, actually about 25% of the photocurrent of this device comes from light absorbed in the fullerene. So that might tell you that you want to actually improve that number and make fullerenes even more light absorbing. That's something that people are working on. So in the model, we incorporate both processes, light absorbed here, light absorbed there. So anyhow, if you compare this device and you look at its band gap of 1.6 electron volts, compare it with the ideal device. So the ideal device is based on a Shockley diode and exponential turn-on diode, from which you can extrapolate the current and the voltage and the fill factor. What you find is that you're losing about 40% in each of the current and the voltage compared to the ideal device. So the loss in current has to come from recombination, and as I'm going to show you, that is due to both the kinetics and the energetics of the system, and the loss of voltage is due to band alignment, which is essentially energetics. So in the end, we lose about 70% relative to the ideal device. So let's first look at the energetic issue, the band alignment. So this is a little more accurate band diagram than what I showed before. Right? So here's P3HT, here's PCBM. So here's a band offset, something like over electron volt. And that is the free energy, the delta G, available to the system upon charge transfer from the polymer to the fullerene. It's a huge loss in the system. Right? You absorb a 2 electron volt photon, you immediately lose 1.2 electron volts. So gigantic loss in our overall efficiency. So basically, this limits your open circuit voltage. So the open circuit voltage is given by this offset here. That's the effective band gap. The HOMO of the donor minus the LUMO of the acceptor. And there's another term there, which is the recombination term. So more recombination means smaller VOC. And that was worked out by Yan on Coaster also in that 2005 paper. The question is, though, do we need this big band offset, delta G, in order to drive the separation of charges? On one hand, you actually like to have that delta G, because that imparts thermal energy to the carriers, which would drive them further apart. So maybe that helps us overcome this issue of the 18 nanometers, right? If the charges have a lot of kinetic energy, they won't like to recombine, instead migrate away. So you might want a large delta G. And if you do a calculation, if you dump 1 electron volt into an electron in whole, you get some ridiculous temperature of the system, like 10,000, 100,000 degrees Kelvin. Right? So a lot of thermal energy there. Okay, so just to wrap up the story, what we did in the recent work was to look at that band diagram in a much more detailed way, and to include not only the band offset delta LUMO, but the delta G from, first of all, hole transfer. So if we absorb a photon in the fullerene, we have hole transfer back to the polymer, so both processes. And also the recombination term. So if you have an electron here and a hole here, there's a free energy gain when they recombine. That's the delta G of recombination. So there's 3 delta G's we have to worry about. And as you shifted the donor with respect to the acceptor, all 3 delta G's will change. All right? And so all the rates of those processes, which depend on delta G, will change. The other thing is that I put in the exon binding energy here, E sub E. So that's something like 0.2 electron volts. And that's, again, this Coulombic interaction between electron and hole. So what we do is take that model and put it into another kinetic scheme, this one more simplified. So we got rid of the charge transfer state just to make things easy. So we've got D star plus A goes to D plus an A minus. There should be a minus there. And then you either get transport out of the device to get free charges or recombination back to the ground state for loss of energy. So the important thing here is this thing called Marcus theory, right? So Rudy Marcus got a Nobel Prize for developing this very elegant theory. And what it says is that the rate of charge transfer goes as an exponent of delta G squared. And not just delta G, but delta G plus lambda. So what is lambda? Lambda is the reorganization energy. So if I have a molecule, I put an electron on it or a hole, all of the bond lengths are going to distort a little bit. And there's going to be a change in the energy of the molecule. So that change is the reorganization energy, including this molecular surrounding, which goes into lambda. So normally we're talking about a process in which delta G is negative if we're combining a hole and an electron. So that means there's a point where delta G cancels out lambda, and actually you get the largest rate of charge transfer. So here's K, here's lambda. When lambda equals negative delta G in this case, this goes to 0, an exponent of 0 goes to maximum, give maximum charge transfer. So that's the model we use for charge transfer in the devices, or in these systems. First of all, you might ask, can we get away with that? Can we use Marcus theory? And that's been a question in the literature for a couple years now. But we think the answer is starting to become more clear, and the answer is probably yes. So I'm just going to highlight a recent paper by Gary Robles' group. It was done largely by David Coffey, who's now moved on to North Carolina. But they were able to measure the charge generation rate using the TRMC, the microwave experiment I talked about. And they did it for a series of polymers. So I know you can't see this, but here's a F8T2, F8, and F8B2. These are 3 quite similar polymers. And vary delta G by using a range of fullerenes. So varying the band offset in that picture I showed you. So sure enough, if you measure the charge generation rate versus band offset, in each of the 3 cases, you see something that looks like a parabola, or what would be the exponent of a parabola, where there's a maximum generation rate, roughly where delta G would equal lambda. So it's not a definitive proof, but it's very strong, rather convincing proof that Marcus theory is appropriate description. So we take that theory, stick it into that kinetic model, pull out things like short circuit current, the voltage, the efficiency, and away we go. So what I'm showing here is the band offset, delta LUMO, and in the blue curve is the current, and the red curve is the voltage, the green curve is the efficiency. Oh, I'm sorry, no. Green curve is voltage, red curve is efficiency. So what you see is as you decrease the band offset, the voltage goes up. That's because the effective band gap between donor and acceptor is larger, you get more voltage. And what you see is in the blue is basically a truncated parabola. That's the Marcus theory coming into play. So here is the rise of the parabola, here's the decay of the parabola, and the truncated part means we're basically saturating the charges. We're getting all the available charges out of the device. So you multiply those two together to get an efficiency. What you find is with a maximum offset of 0.3, you would have about 8% device. And the dashed line here is a fit to the experimental result. It's a fit to that 7.4% device published by UCLA. And so all the parameters fit very nicely. Okay, so this says that if we could take those two materials, decrease the band offset, you would go from 7.4 up to about 9% efficient device. Okay, just by decreasing the band offset. Now, in order to make this fit, we had to assume a rather large reorganization energy, something like 0.7 electron volts. So that means that when you put a charge on the molecule, it undergoes a pretty big distortion, and there's a large energy shift. Okay, so let me cut to the chase here and say, what if we make that lambda very small? And actually, this is a typo. It should be 0.3. So let's make the reorganization energy very small. Make it 0.3. And furthermore, let's optimize the light absorption in the device. So let's make the band gap for both the polymer and the fullerene 1.4, which we think is close to optimal. And make them a little bit thicker so that they each absorb about 90% of the light. Okay, this is fantasy land, but something that we can strive for from a synthetic chemistry standpoint. So when you do this, you get the same type of curve. Voltage increases at smaller offset. You get a truncated parabola for the current, but what you see is increased efficiencies. And namely, if you have a very low band offset, you get efficiencies approaching 20%. Right? So you have high voltage, high current, 20% device. So the bottom line here is, A, Marcus theory seems to describe the system pretty well, and B, if you have a small lambda and small band offset, you might be able to get to 20% device. Okay, so we're at 10% now. Here's one pathway to a 20% device. Any questions on that? I went through it pretty rapidly. Okay, need to wrap it up here. I'm running a little bit over on time. I'll skip the details of rate constants and kinetics and just wrap it up with a couple inspirational strategies for higher efficiency. So I told you one route, optimize the molecules. Another is device design. And you're going to hear a lot over the next couple of days about tandem cells. This obviously is a big topic. This is a review paper in 2009 by Christoph and group. And I want to point out two things. One is that in the organic PV device, you have absorption bands that are a little bit more narrow. They're resonant features, right? So here's a low band gap polymer, high band gap polymer, or small molecule. And what this means is that you can stack these layers in either orientation. You could put the low band gap one on top or put the low band gap one on the bottom. This gives you a little more freedom than an inorganic semiconductor, where these band profiles, absorption profiles, are flat, and then they go to the band edge. So in that case, you don't have complete freedom. You have to put the high band gap component first, in this case on the bottom, to absorb the high band gap light, and then absorb the low band gap light. So in an organic system, you can flip them around. Second thing I want to point out is how to actually make the device from the band structure standpoint. And basically, it's very similar to an inorganic device. You have one junction, lower high band gap, another junction, lower high band gap. You have to combine the two in an interconnect device, which functions as a recombination layer that brings the electron of one side with the hole of another side and add the potentials. So then you can add the voltages of the two junctions. So in one way, it's very similar to inorganic tandems. In another, it's very different. So as I said, many people will be talking about this. I just want to highlight Maurice's work, recent work, using these DCV6T molecules and this stack of materials, and I'll let him go through the details, but he was able to get over 6% device with 2 centimeters per area, so very encouraging. And in fact, the Heliotech 10.7% device is a tandem device, 2-junction device. The UCLA device, 10.6%, is also a tandem, in this case, solution processable materials. So this slide points out that you can do this with both small molecules that you thermally evaporate and with polymers that you can solution process. So it is a very general approach. Another approach to high efficiency. So I showed you before the bulk heterojunction I showed you that the active layer is rather disorganized. Donor and acceptor can be rather amorphous in their morphology. People are now working on the ordered bulk heterojunction. So you make something that looks more like the cartoon there, where there are more direct charge transport pathways. This was done actually a while ago by Steve Forrest's group looking at copper thiocyanine, little nanocrystals. But more recently, his group and the group of Parada and all have done this and are getting quite nice efficiencies out of such systems, 4, 5, 6%. Mitsubishi Chemical, their high efficiency devices, over 10%, also based on the ordered bulk heterojunction. In this case, they're using this porphyrin molecule that is solution processable. They produce it from solution. They then heat it up to make it insoluble, so they drive off the solubilizing groups to create an ordered array of something like these little nanopillars. So in this device, it's published at something like 5%, but as I said, they're getting close to 10% in the recent devices. So just two last concepts. I'm going to skip that for time, but this is basically the outcome of that device. So this is a recent work by Lynn Liu's group in Princeton and Sherry Kagan at the University of Pennsylvania. So what they're doing is incorporating these bulk heterojunctions into a photonic structure. And you heard quite a bit by Sailing Hay about photonic structures and metamaterials last week. So this is basically a quite simple route to get to photonic structures. What they do is they coat the film onto a substrate that they induce some mechanical stress. They induce it by heating it up. And to relax that stress, it folds, it creates wrinkles and folds to get this very nice self-assembled structure. So that creates lots of opportunities for light trapping in the device. And in particular, it creates light trapping opportunities at low energy photons, the low band gap photons. So normally one would create photons up here at higher energy. That would be direct absorption by the polymer. So when you do this, you vastly increase the light absorption at these low energies. So these low energies correspond to the charge transfer state that we talked about. And usually there's very little absorption there and very little current. But when you do this, you can increase it by many orders of magnitude. In this case by, well, 600% in the IR. So our co-chair Yao and his colleague at NREL, Brian Gregg, wrote a comment on this and described what's really happening. And I'll leave him to answer more detailed questions, but the bottom line is that here is the charge transfer state. It's a cross-gap state between the donor and the acceptor. You can excite that directly. If you come in with a low energy photon, you excite this transition. Normally that's very weak. It's not a strongly allowed transition. If you increase the cross-section with the photonic tricks, you can increase that absorption, and that means harnessing the light of these low energy photons, right? The advantage is that when you go to do charge transfer, so now you transfer the charge to the acceptor, there's a very little band offset, very little thermodynamic loss associated with that charge transfer state. So in principle, you can get to much higher efficiencies with that system. So Lynn Liu's work is just the first step in that direction, but we hope to see more efficient materials that utilize that. So CT state. And I've got one more last slide. So one more concept for high efficiency. And this is something Andrew Ferguson also talked about. So the idea is to use quantum coherence. This is a very new concept with regard to organic photovoltaics. It's not a new concept with regard to natural photosynthesis. So a number of people, notably Greg Scholes at the University of Toronto, are looking at quantum coherence as something that plays an important part of the exon dynamics in natural photosynthesis and potentially in organic PV systems. So the idea is that you form an exciton somewhere in your material, and there is quantum coherent states that that exciton can access. And that would mean the exciton could basically bounce around the material very rapidly, more rapidly than it would do so otherwise just by diffusion. So these are calculations of probabilities of excitons that would find coherent states elsewhere in the film, and it would select one of these states and immediately zap to one of those other places. So we have evidence that that occurs, but we have not designed any systems that specifically utilize that. So the idea would be we would design a system to really harness that and to zap the exciton directly to the interface with an acceptor and then extract the charges very rapidly. Right? So another idea that just really coming sort of into play. Okay, so I think I'm well out of time. Let me thank a number of people, my grad students who obviously work closely with, Brian, Alex, Shaheen, Daniel, and AJ. A lot of them work at NREL, some of them work up here at CU. A whole host of colleagues at NREL and funding from the NSF and the Research Corporation for Science Advancement. So I want to thank you for your attention over the last few hours. Hopefully the clickers were not too arduous, and I'm happy to ask or answer any more questions you might have. Yes, please.
We go back to the Marcus
Yep.
stuff for a second. You mentioned you have an offset of 1.2 eV, I think it's 1.2, in a typical device architecture. Is that evenly Marcus normal or inverted region when you're in that, when you have that big offset right now? Or do you know?
Don't really know. According to the recent measurements here, the typical lambda is around 0.6. So here it's 0.6, here it's 0.4, here it's 0.6. So that would put the band offset in the inverted regime at 1 electron volt. Yeah.
Which would be really bad for electron transfer. Right?
So it means that the rate of electron transfer is reduced because you're in the inverted regime. However, it's not just that rate that matters. It's the balance between the rate of forward transfer and the recombination. And the recombination is so slow that you have many orders of magnitude to give away in the electron transfer rate. And so that's borne out in this plot where you see this truncation of the current, right? So here's the inverted regime. Here's the Marcus inverted regime, right? And so pretty quickly you saturate the current. So here you're still technically in the inverted regime, but you get lots and lots of current. Yeah. Yeah, question?
I had a question. So in the beginning of your talk, you showed that these solar cells were operating in the max power points, were operating near the max power point, so the electric field is very small. So you made a comment saying that the influence of electric field, especially on the generation rate, tends to be very weak. But later on in your talk, I think you made a very important point. That the issue is really not the magnitude of the electric field, but rather the distribution of the electric field.
Mm-hmm.
Because when the dark current gets significant, you lose the homogeneity, and then all of a sudden you get charge accumulation, and then your static fraction is some difficulty. Can't you also get that same problem of non-uniform field distribution by, say, for example, increasing light intensity, so you generate significant amount of co-generated charge, or by increasing the active layer thickness, such that you can absorb a lot of light before you generate lots of charge? And in either of those cases, you can have the same non-uniform distribution of the electric field in the light.
Absolutely. So that's particularly a problem for thicker active layers. You always have the Beer-Lambert exponential absorption law. So you're not going to change that shape, but if it is very thick, all the charges will build up on one side of the device. You can get a voltage out of the device that has completely symmetric electrodes just from that effect. There's a name for that, the Meitner effect, something like that. Yeah, where you build up all the charge on one side. So that folds into the design of the device, right, and keeping the layers a little bit thinner if you can. There are no more questions? Time for a coffee break? Sorry, one more.
If I have got charges really full up to some extent, then do not make a difference on the device performance anymore, or do they always stay space?
Yeah, it seems like the more you put in, the worse it gets. So you can't really fill them up, let's say. Now you have to ask the question, where are they coming from? What is the origin of the dark carriers? So frequently it's just oxygen in the device, in which case there's going to be a saturation level of absorption of oxygen in the lattice. But from the device standpoint, more dark charges is a bad thing. Oh, sorry, one more before coffee.
I'm curious to know, is there any difference in the case of charge transportation between small molecule organic solar cell and polymer solar cell?
In terms of the theory, not really. It's the same issue of overlap of HOMO levels and LUMO levels, and the overlap integral between two adjacent molecules, this 0.01 electron volt stuff. The difference really comes in the processing of the materials and what the morphology is that comes out of it. But at a basic physics level, no, there's no difference. Yeah. Oh, sorry, one more.
I have a question regarding reorganization energy. What is the source of this one, and does it affect the exciton dynamics also?
So, yeah, the source of it is literally the changing of the bonds when you put a charge on the molecule. So, for instance, C60 is a very rigid molecule. It's a very strong bonding cage. So you put a charge on it, the distortion is very small. So we don't really know what the reorganization energy is, but maybe 50 millielectron volts, something like this. Does it affect the exciton dynamics? Definitely, right? That's borne out in the decay rates. I didn't talk about them in the model, but there's decay rates for the excitons, there's charge transfer rates, all that's in there. And so yes, it strongly impacts the rates. Okay guys, I think we should probably get a coffee, and I'm sure we'll be around for the next 3 weeks, so thanks a lot.